Hello, welcome back. We're going to continue with brute force algorithms today. In fact, we're going to finish up on brute force algorithms and conclude with a quiz. Don't worry, don't panic. I'll show you what I mean by a quiz. But before we start, there was a question sent to me via email on, just asking for clarification on how you should be taking care of the command line arguments and the file inputs. And so I wanted to run through a very, very quick demo here just to make sure that we're all on the same page. If you need to, you should revisit your Computer Science 1 and Computer Science 2 material on basic input-output, file input-output. If you're doing this in a brand new language, which you should be doing, like Python, then you should be consulting tutorials. How do I do file I/O in Python? How do I do command line arguments in Python? If you're having trouble understanding why we require the run.sh file, again, we don't know what language you're going to do it in. You could be doing it in C++, you could be doing it in Python, you could be doing it in Haskell. We're just going to provide command line arguments that this is the Boggle file that you should be processing. This is the dictionary file that you should be processing it against. Go and do whatever you're going to do, right? That's why we need a common file called run.sh, and it just passes those command line arguments onto your own script. Because the vast majority of people do choose Python for this course, I am going to go ahead and do this demonstration in Python, but of course, if you're using something else, it'll be very, very similar. Remember that we are on Piazza and YouTube, of course. If you have any questions, go ahead and post over there, and I'll occasionally look over, okay? First of all, so how do you do file I/O? I'm just going to start in Python here. How do you do file I/O in Python? There are a couple of ways, input at least. Output is different, and you're not doing output, you're doing output to the standard output. But it's very, very similar to how you would do it in C. You need a file, a handle F, and then you open a file. And I'm just going to open up foo.txt for now, right? If you want the entire contents of the file, you can dump all of those right away by simply just calling this read method. So the contents of the file are going to be f.read, right? That gets you the entire file in one go. There are a bunch of other options here. For example, you can open the file for reading or writing. Reading is the default. That's why I didn't provide any additional arguments. You can also specify whether or not buffering occurs, and I believe that the default is buffering does occur, which is what you want. And then I'm going to close the file, f.close. All right. Okay. So very, very similar to how you would, exactly how you would do it in all programming languages. You open the file, you process the file, you close the file. And let me just go ahead and print the contents of this file. Okay. Now I'm going to go over here to my executable environment here and go ahead and run this as Python 3. I believe that this will work in both Python 2 and 3, but in any case, note here that there is no foo.txt file. Right, and so it ends up being, well, there's no such file, so it quits out. So let's actually create that file, foo.txt, right? And I'll go ahead and edit it over here in Atom.io. Now, there was a question about the Boggle input, what it looks like. That's in the handout, but it might look something like this. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, right? There is a 4x4 Boggle puzzle, right? And hopefully you understand the game. I gave a brief description of it, but you can start at any letter. You can go up, down, left, right, diagonally, and you can form words. So, for example, I can go from F to E to I, but that's not actually a word, right? I don't know if I can form any words here. L-O-P, lop, that is a word, right? If I start at L, go over to O, and down to right to P, then that's a word, and I need to count that and report that, okay? All right, let's go ahead and go back to our script here. If I print the contents now, of course, that file does exist. Oops. I didn't recreate the file, I just updated it. There we go. Python 3 demo, and it just dumps the entire contents of the file to that content string, okay? And another way to do this, let me go ahead and open bar.txt, right, once you've got all the lines, of course, you can split that out, explode it, however, whatever terminology Python uses, and process it line by line. If you want to, though, of course, you can go ahead and do that directly using the following syntax. So for line in f dot read lines, right? Oops. That's going to set up a loop for each line. Let's go ahead and print the line, right? And we'll get some similar result here, except that, of course, again, bar doesn't exist. So let's go ahead and create that file, bar.txt. And just to simulate what you're doing with Boggle, this would be a dictionary where you've got a single word on every single, on one to a line. So lop, hello, computer, science, right? So there's your dictionary, but your dictionary only has 4 words. There are lots of dictionaries out there that you could use. That's why we parameterized this as a command line argument, so that you could use different dictionaries to solve the same puzzle, right? So now let's go ahead and run that, and we get, there we go. Now it's putting extra lines in here because, of course, print is going to be printing extra lines. If you want to format that a little bit differently, of course, you can strip out, I believe it is, right? Yeah, strip the end line characters, a leading and trailing white space, I believe. So we've got lop, hello, computer, science, right? You can get more fancy if you really want to. So let me go ahead and create a variable here, I is 1, and then we'll print a formatted string here, the line number with a colon followed by the actual line. There we go. And then I'll provide this as a tuple, I, and then the line, but stripped. Right? And print, I believe, is putting in that end line character. So we'll go out, and then I, of course, need to increment I, plus plus. Remember, you can't do that, but you can do this, right? Plus equals. There we go. So there's line 1, lop, hello, computer, science, right? That's the basics for your first, the first programming exercise on your first assignment. But I've hard-coded these things, right? If you want to get your scripts to a working point where you've hard-coded the local files, fine. But when you actually hand them in, you need to take command line arguments. In Python, to take command line arguments, you need to import the sys package. Sys short for system. And all the command line arguments are in sys.argv, right? Just like C, argv is an argument vector. It's the actual arguments provided by the command at the command line. So we're going to expect the first file as the first command line argument, which would be argv sub 1, sys.argv sub 1, right? And sys argv sub 2 is going to be the second command line argument. Now, note that it is 0 indexed, so the first command line argument is the script name. That's similar to how it is in C, where it's the executable file name. In Java, it's a little bit different because you don't have the class file is not included as the first command line argument. But for the most part, most programming languages, the first command line argument is always the executable or the script file name. Okay. Let's check this out again. Let's try to run this again. Right. It's not going to work because, of course, I did not provide these command line arguments. Right. So let's go ahead and add some basic error checking. If the length of sys.argv is not equal to 3, then we'll print an error message. Error, provide 2 file names. Right, there we go. And we can exit on them. Right? That's just basic error checking, right? And provide 2 file names. Why 3? Well, again, the first one is that executable file name. The second one is the first file that we want. The third one is that second file that we want. So A, B, and of course here there's not going to be any file named A, B. I want foo.txt and bar.txt, and we get the same behavior as before. Right? That's just the Python way of doing it. There are better Pythonic ways of doing it. Using the with, there's some alternate syntax that you can use, but this is enough to get you started here. The reason that we require you to use a run.sh file is because we don't even know what you're going to name. I named it demo here. You might have named it boggle.py. You might have named it myassignment1.py, right? You might have done it in a completely different programming languages that requires it to be compiled and then run from an executable, right? That's why we provided run.sh example files. And let me just go ahead and produce a new file here, run.sh. They're all bash files, but of course you can change that. Bin bash. All right, so this is a shebang if you don't know what this is. Bin bash. All right. Actually, is there one in user bin bash on my computer? Nope. Okay. So whatever examples we've given you, those work on CSC. I'm only doing this because it works on my computer. That's where the bash script is on my computer. Your computer may be different. You may have to change this when you finally hand this in, okay? But I'm going to run it exactly how I ran it over here, right? Python, the demo file, and then the first command line argument and second command line argument. And let me just go ahead and hard code these initially, right? There we go. All right, there it is running again. But now I can run it through the sh file, right? And I need to chmod it because it's not a runnable file. Our grading scripts take care of that for you. There we go. And when I run this, of course, I get the same behavior because in the script, I am passing these two command line arguments to my Python script. Right? Now, you don't want to hard code your command line arguments. So the syntax for passing whatever arguments we've been giving the run sh file is, I think, yeah, if memory serves, it's like that. All right. So let me go ahead and run this again. And you'll see that I didn't provide any command line arguments to the run.sh file so that it could hand it off to the Python file. But if I do A, B, right now, oops, should have passed those through. Maybe I'm wrong. Maybe it's $, sorry. There we go. Yeah, there we go. No such file A, right? And no such file B if we ever got to that point. But if I want to, I can provide now foo.txt and bar.txt, right? And we get the same behavior as before. So sorry, that's $@. If you just use the examples that we've given you in the GitHub repo, you should be good to go, right? Hopefully that addresses all the issues though and gets you started on file IO. Again, parsing the files, that's not the focus of the assignment. Hopefully you've already got your parser written and done at this point for both of those. You've got the problem in memory for however you want to represent the problems, right? For both the Boggle and the 0-1 knapsack problem. Okay. No questions so far, and everything is looking good. So let's go back to our original content over here. We left off last time talking about the Hamiltonian path or cycle problem. Remember, that is a path in a graph that visits, it's a simple path or a cycle that visits every vertex exactly once. A graph is Hamiltonian if it has at least one Hamiltonian path or cycle. There could be many. In fact, there are. In fact, if there's a Hamiltonian path, A to B to C to D to E, there's at least one more going in reverse, right? So just as a reminder, let's go ahead and take a look at the example that we were running with yesterday. And I'll use my highlighter today. Here we go. Again, you can... nope, I want that. There we go. You can start at A, go to B, go to D, but then you're at a dead end, right? There's nothing else. There's nowhere else you can go, so that does not form a Hamiltonian path. If you want to, you can go from A to D to B to C to E to F, and that does form a Hamiltonian path. There are many Hamiltonian paths in this graph. There are graphs with no Hamiltonian path. So you do the problem is, given a graph with its vertices and its edges, we have to determine, does a Hamiltonian path exist? Okay. So how do we go about doing that? Let's go ahead and start writing. We'll come back to this figure here later. Let's go ahead and start writing some pseudocode here that forms a brute force approach to this problem. So our input will be a graph. G equals V comma E. That's the vertex set, of which there are n of them, and there's an edge set. There may, there's some number of them. Our output will be true if G has a Hamiltonian path, right? Now, variations on this, again, you could have a cycle, right? You could be checking for a cycle instead. Here's a Hamiltonian path. There doesn't, if you also connect the endpoints back to where you started, then that forms a cycle. It could have a Hamiltonian cycle, or sorry, it could have a graph could have a Hamiltonian path, but no cycle because there is no corresponding edge going back. But if it has a cycle, then of course, yes, it has a Hamiltonian path. If you've got a cycle here, all you have to do is take out one of those edges, and you've got a Hamiltonian path connecting all the vertices. Okay. There are also other variations that we talked about last time, where you can have the functional version. Great, it has a Hamiltonian path. What is it? Output at least one Hamiltonian path. Output all the Hamiltonian paths. Count the number of Hamiltonian paths there are, right? Find me the best Hamiltonian path. Whatever that means, if it's a weighted graph or some other objective function that you're trying to maximize or minimize. Okay? So our output is true if it has a Hamiltonian path, and of course, by exclusion, false otherwise. Okay? This should be pretty straightforward for you, at least for pseudocode, right? What are we wanting to, what kind of combinatorial objects are we generating if we want to take a look at a Hamiltonian path? Let's come back to our figure over here. What we looked at last time is, what if I generated permutations? Say A, B, C, D, E, F. That's the identity permutation. Does that form a valid Hamiltonian path? A to B to C to D? Nope, you can't go back, right? So with that permutation, no, that's not a Hamiltonian path. Try the next permutation. A, B, C, D, E, F, right? So A, B, C, you still can't go to D, right? We observed last time that anything that has a CD in it, or in reverse, a DC in it, that's never going to form a Hamiltonian path. Oops. It's never going to form a Hamiltonian path, right? But let's go ahead and be naive and go ahead and generate all of the permutations. You can eventually see that there will be a permutation that gives you a Hamiltonian path. A, D, B, C, E, F. At that point, you can go ahead and stop and report yes. That's the first Hamiltonian path I found. The variation that we're looking at right now is not find all of them or count all of them, but you found one. That's good. Stop. You're done. Yes, there is a Hamiltonian path. So, pseudocode, how do I generate all permutations? That algorithm from last time. That's not the focus of this algorithm this time. So all I'm going to do is use the power of abstraction with respect to pseudocode to say, for each permutation of vertices, and usually permutations are labeled with pi, and I'll label this as v1, v2, ... vn. Remember, in general, n is used as the number of vertices in the graph. We're not permuting edges. Because if we were wanting to do a brute force solution for like an Euler path, then we would be permuting a bunch of edges. But here we're permuting vertices because we're going to visit every vertex exactly once. And an edge can end up visiting, like in an Euler path or Euler cycle, you can end up visiting the same edge vertex multiple times. All right. So for each one of these, we need to verify whether or not, and I'll put it in comments here, verify if pi is a Hamiltonian path. Well, we already know by how we constructed it up here that it includes all vertices. So we already know that if it forms a valid path, then it's a Hamiltonian path because it has all the vertices there. So let me go ahead and rephrase this and say is a valid, valid path. Dot, dot, dot. How do we do that? We just have to check vertices, right? So for edges, sorry, excuse me, for I running from 1 up to n minus 1, right? Actually, give myself some more room here. For I running from 1 up to n minus 1, I just need to make sure that each one of these vertices, v1 to v2, that's a vertex. v2 to v3, that's a vertex, or edge, excuse me. v3 to v4, that's an edge, dot, 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 all the way up to the last one here. I need to check to see that that's an edge. That's why I stopped short. I don't want to go up to n and then compare it to n plus 1, because that would be off, an index out of bounds, basically, for pseudocode, right? So if v sub I plus 1, right? If that's in the edge set, right, then it is a valid edge. Continue and move on to the next one, right? If it's not in the edge set, then it is not a valid path. Is valid. That's why I left myself some room up there. I'm going to set that as a flag value to false, right? And I'll initialize it to true. Is valid is true. All right? We'll assume that it's a good path, and then we'll go through it and verify that it is actually a good path. If we ever see that, no, v1 to v2, that's not an edge, then we'll go ahead and report that as a false. All right? Now, at the end of this loop, we've only verified that one permutation. If that permutation is not is invalid, then it's not then that doesn't mean that it's not a Hamiltonian path, right? Just like over here when we looked at this permutation and this permutation, those didn't form a valid path, but we went on until we found one that did. So we need to go on to the next permutation, but if it is a valid path, we need to stop and say, we're done. We found a Hamiltonian path here, right? So if is valid, stop and output true. Otherwise, if you get through every single possible permutation and none of them forms a valid path in the graph, then you know that there is no Hamiltonian path. Right? And of course, variations on this would be if it's valid, then and you want to count them, then you'd increment a counter. If it's valid and you want the functional version, I don't care what, I know that there's a Hamiltonian path in there because it's a complete graph. Give me the best one, right? Go through them all until you find the best one. Or is there a Hamiltonian path? Yes. Okay, well, what is it? Well, here you go. Output the actual path, right? In this case, pi, rather than true or false. Remember, those are the differences between decision versions of a problem and functional versions of the problem, optimization versions of the problem, counting versions of the problem, etc. That'll come into play later on when we start looking at NP completeness. Again, that was kind of a naive solution, right? Why would you go through every single permutation? In this case, there are going to be 6 factorial permutations, wherein the vast majority of them are not going to be valid. Anything that contains CD, anything that contains AC or CA, anything that contains DE or ED, right? All of those are going to be invalid, and we don't even have to check them, right? This naive solution here is running through every single possible permutation when it doesn't have to, because it's a blind brute force algorithm. It's not taking the structure of the input or the structure of the problem into account. It would be much better if we did that. For example, what if we just started at, say, B, right? We'll start at that vertex. And we look at the neighborhood. We kind of previewed this last time. We look at the neighborhood of B, and we see that we have a lot of possibilities here. We could go to A, we could go to D, we could go to C, or we could go to E. And I'll just go ahead and write those in lexicographic order here. A to C, or we could go to D, or we could go to E, right? Can we go to F? No. And consequently, that never ends up in our computational path there, right? Effectively, by only looking at the neighborhood, only looking at the actual structure, we call it topology in graph theory. By looking at the topology of the actual graph, we can, start pruning things out. We can start, getting rid of invalid solutions immediately. All right. Now, let's go ahead and suppose that we started at B, and then we followed this computation path, right, where we went over to A. Right. Now we're looking at the neighborhood of A, and we're saying, all right, well, I'm looking at B and D here, but I've already come from there, right? It's highlighted here. So I really only have one choice. I go down to D. Right? Now, following that computation path, I look at the neighborhood of D, and I see that my neighbors, A and B, are already in the computation path. I'm at a dead end, right? This dead end resulted in no Hamiltonian cycle, or a Hamiltonian path, excuse me. Right? So we backtrack, right? End up backtrack here. We were there before. We went from B to A, but now I've exhausted the entire neighborhood of A already, so I backtrack up to B, right? And I'm at B now, and I follow a different computational path down to C. All right, let's go ahead and follow C. Right? Now I'm at C, and I'm looking at its neighborhood. Right? Its neighborhood consists of B, E, and F. But I already came from B, so I'm not going to consider that as I move forward here. But I will consider that you can go to E and you can go to F. At this point, I'll draw your attention here to the fact that we've got E repeated several times in this computation tree. All right? That's perfectly fine for this problem because we do need to exhaustively search all paths. Later on, when we look at graph algorithms and we're basically doing what's called a DFS, a depth first search here. When you do an actual DFS, you don't want to re-explore parts of the graph multiple times like I'm doing here. I'm going to E here and I'm going to E here. In fact, I'll be going to E several times throughout this. I don't want to do that in a regular depth first search. But here it's fine because I am searching for a Hamiltonian path. Okay? Let's suppose that I went to E and I look at its neighborhood. Well, again, B and C are already in my computational path here. So my only option is to go to F. Right? At which point, let's follow that. Its neighborhood has already been explored. C and E are both in my computational path here, C and E. That's where I came from. It's a simple path, remember. You don't want to traverse things more than once. At which point, I'm at a dead end, but is that a Hamiltonian path or not? 1, 2, 3. Nope. That's a path of length 3. What do I need in the Hamiltonian path? 1, 2, 3, 4, 5. Right? For this particular example, because there are 6 vertices. Okay? Likewise, let me go ahead and fast forward here. From F, you would only have one choice, E. If I went to D, I would only be able to go to A. If I went to E, I would be able to go to C or F. Right? And from C, I would be trapped basically, and I would have to go. I would go to F, and I would go to C. Right? None of those resulted in a Hamiltonian path, but we already know that this graph is Hamiltonian. So why didn't this work out? Well, because you started at B here. B is kind of what's called a bottleneck, right? That it's sorry. Let me put that on ignore mode. There we go. Right. No cell phones in class, right? Anyway, we started at B here, which is kind of a bottleneck. If you go to this direction through the graph, well, then eventually you would have to come back to B in order to go over to that direction of the graph. So just by looking at this, we humans could see, well, if there's a Hamiltonian path, there's no way that it's going to start at B. So, nope, wrong. But a dumb computer, of course, would have to exhaustively try all possibilities. So what I'm saying here is that this way of approaching it, right? you need to do your Hamiltonian path could start at any vertex. It could start at A, and we've already seen that there is a solution that starts at A. It could start at B, D. There are solutions that start at D. It could start at E, F, C, etc. So you may have to restart this algorithm over with a different starting point, D or A or E. Right? If you started it out at A, right, and you went to, and I believe we did this, but here's B and D. Right? If you went to B, you'd be sunk because that's your well, no, yeah, you'd never be able to get back to D. But let's go ahead and write out what the tree would look like, this computation tree. You could go to D, or actually, let me go ahead and go to C and D, right? I'll go in order there. If you went to C, then you could go to E or F. From there, you would then be stuck by going over to the other one, in which case you've got a path of length 1, 2, 3, 4 for either one of these. And you say, no, that's not a Hamiltonian path. But with D, if you went to D, then your only other choice is to go to B. From B, you could go to C or F or E, excuse me. Supposing you went to C, you could go to E or F. And from there, you could go to F or E, but you don't need to, right? Why? Because you're done. This computational path, 1, 2, 3, 4, 5, 6. Oops, I think I've got a, I went to C to E, no. A, B, D. Okay, yeah. 1, 2, 3, 4, 5, 6. There are, I've got something repeated here. I'm not immediately seeing it. Oh, you know what? Sorry, I should have done this off. So what? You know what? Let me go ahead and fix my mistake here using the magic of GoodNotes. There we go. All right. And there we go. I meant it to go off of that one. And that way I've got 1, 2, 3, 4, 5. Hey, cool, right? But the point that I'm trying to make here is that there are other computational paths over here that don't need to be explored because you already have a yes answer down here, right? What does that look like? Here's my input. What I'm going to do is I'm going to come up with a backtracking solution, a recursive backtracking solution, okay? Which means that suppose that I've already jumped into the algorithm. I'm at, I came from somewhere, right, here's a path, and I'm at this current vertex, V sub k, right? And I've got this entire path here, and I'll label it V1 ... VK that I came from, right? This is where I came from. I don't want to backtrack to any one of those vertices. I only want to look forward, right? So my input is going to be a graph, G equals V comma E. This is very common with induction. This is very common with recursive algorithms. What you have to do is you can't think of, the first thing that you think about is not the beginning of the algorithm, but jump into the middle of the algorithm. Suppose that I've already constructed a path so far. What else do I need to do now for the next step? That's why it's inductive, right? You don't you don't start with the base case. The base case you can eventually do that later on. You start out with the case for k. This statement is true for k. I need to prove that it's true for k plus 1, right? Jump into the middle. What do you need? What information do you have? And what's the next step for producing the next piece of information? So my input is going to be a graph and a path, and I'll call it P, consisting of vertices V1, V2, ... Vk. What's the length of this path? Well, it's k minus 1. Okay? And we know that this is a valid path because we wouldn't have gotten to this point if it weren't. And we're going to construct that here. Right? And we're going to output true if G has a Hamiltonian path. Don't worry about false yet. Right? Remember I said that you might need to restart this algorithm? This is just the recursive subroutine What we're going to want to do is we're going to want to also create a main, kind of a main function. I don't want to call it a main method, how do we get this entire recursive process started over? How do I start at B? Oh, I need to restart at A. Oh, I need to restart at C, right? We're going to do that outside of this subroutine. This subroutine is just jumping into the middle of the algorithm. Okay. All right. So how do we know, what's our base case here? How do we know that this path here has already formed a Hamiltonian path? Well, if it has length n-1, or if the path itself consisting of vertices consists of all of the vertices, implicitly there are k vertices here, so we know that it's a Hamiltonian path if k is equal to n. Output true. This is checking that the path has n vertices, right? And if so, you've visited them all. By nature of what we're going to write here now, that we're never going to repeat a vertex, right, in the same path. Okay. Otherwise, again, now look at this from the perspective of I'm at VK. What's my next step? I'm going to look at the neighborhood of VK, right? And there might be things coming out of it. There might be 1, 2, 3, 4 vertices coming out of it, just like we visualized over here, right? And I'm going to run through the each one of those needs to be visited, right? So for, and what do I label it as? Oh yeah, x. X in the neighborhood of VK, right? Do the following. My path will end up, let's go ahead and visit that vertex. If this is x over here, let's go ahead and go from VK to that vertex, forming a new path, right? So P, and I'll just use and abuse the plus sign here to go to the next vertex. In fact, I'm going to relabel that prime, right? And then I'm going to label this entire algorithm. Unfortunately, I didn't leave myself enough room, but you know what? Let's do that trick again. Let's move it down, and let's call this, what I'm doing here is walking. So it takes it takes in a graph and a path P, right? And I'm just giving it a label because I ultimately want to recursively call it on the same graph, but with this modified path, right? And yeah, by virtue of us outputting true here, then we don't need to return anything. That represents the termination of the algorithm and the output of true, right? Of course, if you're actually programming this, you would need, you don't want to go exit, right? Like we did with our demonstration earlier, right? That we exited if you didn't give enough command line arguments. You'd actually want to return this value or set a global or variable or something like that. Don't do that. Globals are evil, right? But by virtue of pseudocode here, walking into the graph onto the next vertex sets us up, and it'll eventually output true if it in fact represents a Hamiltonian path. All right? Got to be careful here. Remember this example. Once I go from A to B to C, right? From C, I don't want to go back to B, right? That would be a non-simple path. When I considered the neighborhood, I only looked at things that had not been formed on the path yet, right? So A to B to C, I'm looking at the neighborhood of C here that includes B, E, and F. But I only went to E or F because B was already visited. We need to take that into account in our pseudocode here. So using the magic yet again, I'm going to give myself some more room and modify this that I'm only going to go to that vertex if it's not already in there. If X is not in the path P, then do this. Right? There. And that's it, right? What about the false case, right? That's, well, again, this is a subroutine. This is the walk subroutine. What I need to do now is I need to create another algorithm that uses that as a subroutine. Basically, this is why you write functions in code, so that you can reuse them and you don't have to put everything in one big giant, function, everything in the main or something like that. Same thing with pseudocode. In our pseudocode for, where is it? There it is. For our pseudocode for generating permutations, did I put in the details of that algorithm that we developed yesterday? No, I relied on pseudocode to do that for me. I can also, I can also call like I think we did maybe 2 days ago. I just had a line there that said sort the remaining vertices or sort the remaining elements in the permutation generation. I didn't say, okay, well, here's insertion sort. It has 2 for loops and whatever. No, I left that off because that was not the focus of the problem. Right now, the focus of this problem right here is that given a partial path, how do you form the next step, right? What I want to do now is create the main for this, right? So let's go ahead and label it as ham path main, right? There we go. And my input here is not going to be a partial path. This is what's going to be responsible for kicking the things off. So the input is just going to be a graph. G equals V comma E. And I'll output the same output here. True if G has a ham path. False otherwise. Right? In fact, if you want to, you can. Yeah, I didn't say false over here in the subroutine because I left it for the main routine over here. So now, again, the idea is that you could start at one vertex and it could fail to give you a Hamiltonian path. So we need to restart at another vertex, right? That's not the same for cycles, by the way. If you start at a vertex and it does have a cycle, it doesn't matter which one you start with because it's a circle, right? A circle has no beginning, no end. But a Hamiltonian path, a path does. It has a beginning and an end that doesn't necessarily go back in on itself. So we may need to restart here. So for each vertex V in the vertex set V, in fact, let me label it X in V. So because the capital V can look like a lowercase v when you've got crappy handwriting here. What I'm going to do is I'm going to call my walk routine. If I walk on the graph G starting at vertex X, a path of length 1, right? If I'm starting here, or I'm starting over here, or I'm starting over here, right? You can have a path of length 1. It's just a vertex, right? So if this walk reports that yes, there is a Hamiltonian path that starts at X, I'm done. I don't need to examine any of these other vertices. All I need to do is output stop and output true. Now here's where the false comes in. If you start at that vertex and there's no Hamiltonian path starting at it, then you start at the second vertex, there's no Hamiltonian path, third vertex, fourth vertex, ... get through all the vertices and there's no Hamiltonian path, that's when you can return that there is no Hamiltonian path, right? Okay. No questions? What about analysis for this? Unfortunately, this is kind of difficult to analyze exactly because it corresponds to the number of distinct paths in the graph in the input. You could have a very simple graph, like a line graph, right? Right, and there are only a couple of lines there. You could have a very complex graph. You could have a very dense graph, like a complete graph, in which case there are n factorial possible distinct paths on that, right? So it entirely the analysis, it's going to defy exact analysis in that it depends entirely on the input how fast this algorithm executes or how slowly it executes. But remember, big O analysis is the worst case scenario. What's the worst case scenario here? That we end up generating every single possible permutation just like we did before. They're all, but it's unlikely that that is going to happen, because if you end up generating every single possible path, then that means that you have, with this algorithm, then that means that you have a complete graph, in which case you would have very quickly stopped an output true, because the very first permutation that you tried would have been a valid Hamiltonian path. So maybe you get unlucky and you'd only do half of them, right? N factorial over half. But it's still going to be order N factorial, right? As a upper bound here. I think that a more careful analysis, you can actually get this down to exponential. Maybe by observing that if it's very, very dense, then that means that there is a Hamiltonian path, and the algorithm will actually execute in a very, very relatively quick time. But if it's somewhere in between those two extreme cases, then it can be shown to be exponential. It doesn't matter though, right? We know that this is going to be super, super slow, right? Last semester, or last summer, I guess, and a couple summers since, or a couple summers ago, maybe I've done it often. I actually assign this problem, right? Where we give you a graph input and you have to find out whether it's, or not it's Hamiltonian. We constructed those specifically to either be small or to be large graphs, but that definitely had a Hamiltonian path that you could find very, very quickly, or as far as a computer goes. But if you've got a very complex graph that may have only one Hamiltonian path, you're looking at a very, very large haystack with a very, very small needle, in which case you might be centuries or the heat death of the known universe to actually execute on your computer. Right? I still covered this algorithm for a very good reason. Right? Think about your assignment where you're actually doing Boggle. In fact, let me go ahead and stay on the iPad here, right? Where you've got this Boggle game. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, right? Now, you're not trying to necessarily find a Hamiltonian path in this, but this is a graph, right? It's kind of what we call a grid graph, right? So consider these as nodes that are immediately connected above, below, and of course diagonally as well. But you can't go from A and jump down to P, right? So we're not going to draw those edges, right? So it would be a graph that looks something like this. Now, every path in this graph corresponds to a potential word. For example, you could start, undo that, sorry. Start at A, go to C, go to J, go to G, right? And you ask, does A, C, J, G, that's a valid path, certainly, but does it form a valid word? That's when you go to the dictionary. Does the dictionary contain this word? And by the way, make sure that you are using something smart like a map or a binary search or something like that to check to see, because your dictionary is going to be like 300,000 characters, 300,000 words or something like that. If you take a naive approach of, is this it? Is this it? Is this it? Is this it? No, that's not going to work. Use binary search to see, does this word exist in my dictionary? Make sure that you're only processing the dictionary file once. You load it up into memory and that's done. You don't reload the file for every single possible word. It will never execute within the 5 minutes that you're given on the grader, right? Much less go on to the next test case, right? Let's see. I'm going to have to erase that. I'll use a different color. There we go. Another path would have been start at L, go over to O, go over to P. All right. So this is very, very similar to finding paths, enumerating all of the paths in this kind of grid graph right here, right? But instead of saying that, well, is this a Hamiltonian path on each one? You say, okay, well, here's the word that's formed so far, concatenate, 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 right? And then take off the last one that you looked at. You're comparing that against the dictionary and saying, yes, that is a word. Put that into memory so that I can report all of the words of length 3, all words of length 4, all words of length 5, etc. Right? So using a very, very similar solution to what we just did, where you restart. Sometimes you'll start at A, or you could restart at B, or you could restart at C, or you could restart at D, right? Then explore every single possible path, making sure to never go over the same letter twice. Because if you were allowed non-simple paths, then I could have D, G, H, G, H, G, H, G, H, G, H, G, H, and I would never stop, right? We also gave you some very helpful hints on how many possible paths there are, how many possible word paths there are, so that you can make sure that your program is actually visiting every single possible path. Go ahead and check out that should be a debugging tool. Am I actually visiting every single possible word, right? And of course, you're only reporting words of length at least 3. We're not going to report, ba or ob or whatever. You have to have at least 3, so you can ignore all paths of only length 1. You need paths of length 2 or more to form 3 letters. And of course, you're limited by the 16 characters here, right? The 16 characters, and you could have repeats. It doesn't matter, so that you could spell egg, right? You could have 2 G's here, but you can't use the same G over. But words at most 16. So there's another optimization you could look for. When you load up your dictionary, if you've got a word with more than 16 letters, throw it out, right? So you can make it a little bit even faster, right? Okay, any questions? I accidentally printed the dictionary times number of lines in the dictionary while doing this. Been going for about 5 minutes. Exactly. Let's see. I printed the dictionary times the number of lines of the dictionary while doing this. Yep. You've got an order n squared algorithm there. 300,000 times 300,000. Good luck, right? Yeah, don't do that. Okay. Let's see. So let's talk a little bit more about combinatorics, right? Right? You can also generate general K permutations is what we call them, right? So for that, let's go ahead and go back over here to the iPad and show you what I'm talking about here. Right? So K permutation, if I have elements A, B, C, D, right? How many permutations are there? 4 factorial, which is going to be 24, right? A, B, C, D, A, B, D, C, dot, dot, dot. I'm not going to write them all down. But more generally, what if you don't want all of them? I've got Alice, Bob, Cheryl, and Diane, and I want to arrange them for a photo, but I only want pairs, right? I only want at most 2. I want to do a 2 permutation. In other words, how many arrangements of 2 people from a group of 4 are there, right? And, well, not just how many are there. That's, of course, n permute k in general, right? Where this is n and this is k, right? It's a general k permutation. You don't want to permute them all, right? If you did, then that would be an n permutation. Permutation of n. I want to include all of them. Here I only want to include 2. For example, A, B, right? I could go also B, A. I could go with A, C. I could go with C, A. Right? I could go with a D or A or D A. There we go. Dot, dot, dot. How many possible permutations are there of just two of them, right? Well, that's this expression over here, and I'll let you look that up. That's not part of this course. It's just combinatorics review from, say, 235. But how do we do that algorithmically? How do we actually generate these things? Well, hopefully you saw a pattern here. What I did is, well, okay, go ahead and choose the first two, and then permute them both. Then choose the second two, A and C, and then permute them both. Right? It might help to look at this from the perspective of a little bit larger one, 3 permutations. Choose 3 of them, A, B, C. Now permute all those. A, C, B, B, A, C, B, C, A, C, B, C, A, B, and C, B, A, right? There's all those. My first step, though, was to choose the 3 that you wanted to arrange, and then I arranged them. So how do we generate these things? 1, generate a, and I'll call it K combination here from the set A. Again, we were just calling this A. Right. So given a set A of elements, generate a K combination, right? Then 2, permute the K combination. And let me give this a label, right? I'll call this just a set, so S, which is a subset of A. Permute or enumerate all permutations of S, right? That's it. How do we do these things, right? We did this on Monday or Tuesday or something, right? We gave you an algorithm for generating combinations. Take that combination as a set, a list, whatever, and hand it off to the algorithm that we looked at yesterday. And by combining those 2 algorithms together, you've solved the more generic problem of generating K permutations. There's another scenario of generating permutations with repetition. Right? For example, the classic example is going to be DNA sequences. Adenine, guanine, trypsine, or thymine, AGTC, and cytosine, right? How many possible DNA trigrams are there? Well, you could go with AAA. Trigram meaning that you take 3 of these amino acids or whatever they are, proteins, whatever, and you arrange them, right? AAA. You could also have AAG, AAT, AAC, right? You could have AGA. You could have AG, G, right? You could have A, dot, 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 dot. I'm not going to write them all out. Why? Because there are, for the first one, you could have 4. For the second one, you could have 4. For the third one, you could have 4. And that's going to be 64 possibilities there, okay? There are 64 possible trigrams. Many of them will translate to the same protein or amino acid. Yeah, that's proteins. But you get the idea. You're allowed repetition here. This is an arrangement. AAA or AAG is not the same thing as GAA, right? Those 2 are not the same permutations. But you are allowing repetition. AAA. A is repeated 3 times here. It's repeated twice here. G is repeated twice here, etc. So how do we do this? Right? Well, here's a hint. Let's do it in the most simple of cases when we've only got 2 elements. Instead of A and G, AGCT, let's suppose that we have 0 and 1. Right? And let's go ahead and generate all trigrams related using those. Right? So 0, 0, 0, right? 0, 0, 1. Note here that I'm allowing a repetition because 0 is repeated 3 times. And 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, oops, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. There are only 2 possibilities for the first one, 2 possibilities for the second one, and 2 possibilities for the third one. 8, I've got them all. Right? So hopefully you saw my pattern there. What was I doing? I was counting in binary. Right? So all I need to do is count for this particular example from 0 up to 2 to the n minus 1 in binary, in base 2, and you've generated with of course leading zeros, and output each one. Right? What does that look like with respect to the DNA sequences? Well, that's the same thing. It's just base 4. Count 0 up to 4 to the n minus 1, right, in base 4. In other words, use 0, 1, 2, and 3. Right? Associate 0 with A, 1, 2, and 3 will be associated with G, C, and T. Right? So if you've got a, I don't know what you would call it, base 4 string of length 3, using 0, 1, 2, and 3, then you just translate these to A, G, C, T, respectively, output it, and you're done. Right? Now, of course, again, it's exponential, right? But if you're doing brute force and you're generating all these things anyway, then you've resigned yourself to being exponential. In general, base B, right? If you've got B elements, then this becomes B, and you count in base B, right? Generally, what I would do if I were to actually program this is I would still just count with a regular old integer variable, 0, 1, 2, 3, 4, and use something built in to convert it to base 4 or base 8, right? Usually there's something built in that'll convert it to a string. You do need to make sure that it's padded out with zeros, but otherwise that's the idea. And then you map that back to whatever objects you're actually trying to permute with repetition. Okay? All right, so that is generating permutations with repetition. And I'll just put in the notes here. Remember that we did this with binary strings and, say, DNA sequences, etc., right? Where you can actually repeat things. Okay. Instead of maybe I'll save some of the other problems. At this point, you have enough to certainly get done with assignment 1. We've basically covered everything that needs to be covered. But I will go ahead and talk a little bit more about some more problems on Friday. And then we're going to call back to what we've just been doing of, oh, here's a problem. What off-the-shelf terrible brute force solution could we bring to bear to solve this problem, at least as a first try, right? Most of these problems that we're going to introduce are NP complete or NP hard, in which case there is no known efficient solution, just heuristics or whatever. But I'll save that for Friday. What I wanted to do with the rest of our time today is a quiz, like I said, right? So again, don't panic. Normally, before this course was online, which is a few years ago now, every Friday we would take the last half of every Friday to give quizzes. We usually had 4 quizzes. Last time I did this was summer of 19, as you can see. But since we're online now, and I'm going to be online for this course going forward every summer, If I can help it, if I continue to do it, then I cut the quizzes. We do have the 2 exams that you have to pay attention to, but we cut the quizzes. So what I've done instead for the last couple of years is I've taken the quizzes and I've used them as a review, and we go ahead and do them here. And I've got a whole repository of other quizzes if we really want more practice. But otherwise, let's go ahead and just do one quiz, the quiz from 2 years ago here. So number 1, suppose that you have an algorithm, exists path. This is kind of like a function. Consider this as a library function or a package that you bring in from Python, right? That you can call, which takes a graph G and an integer K and returns true if G contains a path of length K and false if it does not. We don't know how this works, right? Just like, do you know how the square root function in the math library works? No. Do you care? No, because it's been abstracted away. Somebody else wrote that. That's not the problem I'm trying to solve. I'm trying to solve quadratic equations or whatever. I just need the, or I'm trying to solve the 2 closest pair of points. I just called the square root function. I don't want to have to worry about that stuff. Likewise, how does exists path work? I don't know. It just does. Given a graph G and a K, it returns true or false. That's like a Boolean function. It returns yes or no, true or false, right? It doesn't actually, if it returns true, that doesn't actually give us the path of length K, right? It only says, yes, there is a path of length K, okay? That is the scenario. A, using that as a subroutine, write an algorithm to solve the following problem. We're going to provide good pseudocode, but we don't need to analyze it, at least for this. Why don't we need to analyze it? Because I didn't tell you what the runtime of exists path is. It's actually going to be exponential, probably. Given the graph G, output the length of the longest path in G, right? So this is a difference, what I was alluding to before, of a decision version, yes, no, true, false, versus an optimization problem. Given graph G, output the length of the longest path in G, right? The longest that's our optimization objective function, the longest path, right? All right, so hopefully it's pretty. The quizzes were never designed to be all that hard. It's just that some people just have a hard time getting past the fact that it's pretty damn simple solution, right? So here's my input. Oops. Remember, the input is just a graph, not K, right? My input is a graph. G equals V comma E. And what we can use exists path as a subroutine here. But where our output is going to be K, the length of the longest path in G. Oops. I'm already regretting this, but I've got magic, so there. Regretting that I didn't give myself enough room up there. Okay, let's call this longest path. And the input is a graph G. Okay. How do we go about this? Well, you could ask, does this graph have if I'm going to use exists path, right? I could say, well, does there exist a path of length 1? Does there exist a path of length 2? Does there exist a path of length 3? ... Does there exist a path of length n? Does there exist a path of length n plus 1? What's the problem there? Remember that if there's a path in a graph, then it is at most n minus 1. Otherwise, you've got a cycle, or you've repeated a vertex somewhere. You can't visit. If you've only got 5 vertices, you can't have a path of length 10 without necessarily visiting one of these more than once. So all I'm going to do is a for loop for k running from n minus 1, not n, because there would be n vertices in it, but only 1, 2, 3, 4 n minus 1 edges in it, right? If exists path of G comma K. If that's true, output K and be done with it. Because I started at one the longest path over here, and I guess I didn't tell you go down to at most 1, right? Dot dot dot. Right? For K running from the potentially longest path down to the shortest path. Now again, if this says no, there does not exist a path of length n minus 1, that's fine. Then we go with n minus 2, n minus 3, n minus 4, n minus 5. Until we output something. I don't need anything right here. Why? Because trivially there will be at least one path of length 1 unless it's unless the edge set is empty, in which case, okay, fine, we'll go down to 0, right? And that outputs K, the longest path. Okay. Part 2 on this, using exist path as a subroutine, write an algorithm to solve the Hamiltonian path problem. Provide good pseudocode, but you need to not analyze your algorithm. Again, ham path, G. I'm not going to repeat the input. Actually, I could repeat the input and the output. Copy. Paste. Nice. I love this thing. Anyway, output true if G has a ham path. False otherwise. Well, all I need to do is use exist path. What's the length of any Hamiltonian path? N minus 1. So output exists path of G and n minus 1. If that says no, there does not exist any path of length n minus 1, that means that there's no Hamiltonian path. If it says yes, there does exist a Hamiltonian path of length 1 or of length n minus 1, then it does have a Hamiltonian path. Right? It's as simple as that. Implicit with this with these exercises is what's called reductions. That you can take a solution for one problem and use it to solve a similar or variation on that problem, right? Here I'm using the solution to this general problem of given a graph and a k and k, does there exist a path of length k? I could use that to solve the longest path problem, and I can use that to solve the Hamiltonian path problem. In fact, you can use the longest path problem to solve the Hamiltonian path problem. I'm reducing one function to another. And I like to introduce it like this without you knowing, but now I'm telling you, so spoiler, but I like to introduce it like this because unfortunately the way that reductions are usually presented are as these mathematical things that you have to understand, math, when in fact you understand it immediately coming out of Computer Science 1. A function calls a function calls a function. That is a reduction. Right? When you can use a function to solve another problem, one of those problems reduces to the other problem because you've already got it solved. Right? And that's why I like to introduce it this early, implicitly at least. Okay. Part 2. Let G be a graph. A triangle in G is a set of 3 vertices that are all connected. Right? Hopefully you understand that it's just, a triangle. Here's vertex, 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 and they're all connected. Okay. Write an algorithm that, given a graph G, determines how many triangles it contains. Give a full analysis of your algorithm. Right. So my input, there we go, will be a graph G equals V comma E. Right. How many triangles are there? So this is kind of a counting problem, right? Not a decision problem where you say yes or no. Yes, it has a triangle. No, it does not have a triangle. Okay, that's great. I want to know how many there are, right? I'll output the number of triangles in G, right? This is pseudocode. right? Now, what kind of combinatorial objects are you going to want to generate if you were to actually program this? You would want to generate triples. You might want to put on your simple programmer hat and say, I need 3 for loops. For I running from 1 up to n minus 2. For j running from I plus 1 up to n minus 1. For k running from j plus 1 up to n. There you've got your triple right there, right? I, j, k. The magic of pseudocode is we just have to, say for each triple. For each triple. A, B, C in the vertex set, right? Now we need to verify that these 3 vertices actually form a triangle. So if A, B is connected, that is an edge, and I'll go ahead and use the old school or the mathematical caret here. That's and. If you want to, you can go ahead and say and instead. Right? I'll go ahead and go with and here. A is connected to C. Note I don't need to connect C to A because these are unordered pairs. And B is connected to C. Then my counter, I'll increment it. I should have set it to be 0 at first, and I'll simply just output the count. Right? That's all you need, right? All you're doing is iterating over every single triple. We know how to do that because we can use that other algorithm that we developed to generate combinations of 3 from a set of size n. Or you didn't need to hard code 3 for loops because this is a pseudocode. When you went to go to Python or something, sure, you're going to have to type out 3 loops, or you're going to have to use the algorithm that we already developed, right? But this is pseudocode. I don't have to worry about those details. Okay? Here's the analysis. 1, what's the input? It's going to be the graph G. 2, what's the size of the input? Now, with graph algorithms, you have both a vertex set and an edge set. And both of those things together are the input, yes. But it's really, really helpful if you can focus on one or the other. The size of the vertex set or the size of the edge set. At the end of the day, it really doesn't matter because the size of the edge set is bounded by a polynomial in the size of the vertex set. There are at most order n squared edges in a graph with n vertices. So I'm just going to say the size of the vertex set n. Right? And again, hopefully most of this is review from, say, 235, right? Discrete math. 3. What's our elementary operation? I'd say checking on edge, right? This predicate right here is A, B, an edge, right? If your graph representation was a matrix, an adjacency matrix, or if it were a list, that would have different, different complexities. But I'm going to say, well, whatever that is, it costs me 1. It costs me $1 to ask whether or not there is an edge. It doesn't matter what the underlying representation is. It just costs me one thing. That's what an elementary operation is, right? 4. How many times is the elementary operation executed with respect to the input? It is equal to the number of triples, right? And hopefully from combinatorics, you remember that that's n choose 3, right? And you can leave it in that form, but if you really want to, you can expand it out n times n minus 1 times n minus 2 all over 3 factorial, which is just 6. Right? But the really important thing here is 5. Tell me what that is. That's order n cubed. Right? So counting the number of triples is going to be not all that efficient, but not all that helpful either. It's just a made-up thing. It's just a made-up problem. Actually, there are special types of triples called asteroidal triples that give you a lot of structure for graphs and graph theory, but we won't get into that. But that's enough for 25-point credit on our quiz here. Okay. once I wrote it out, another thing that I would note here is this being order n cubed, you're in obvious land unless you're asked to actually produce a proof that this is true, and you can set up a limit proof or you can set up a definitional proof. Then this is what I like to call it obvious land. You don't have to provide a full proof for something like that. But of course, if you're unsure, go ahead and please continue posting on Piazza. Do we have to do this? Do we have to do that? Right? And we'll clarify. This is very close to a problem that I would have introduced if we had more time, that I'll introduce instead tomorrow. But it's called the clique problem. Right? CLIQUE. A clique, I don't know if a group of people is kind of cliquey if they all these four people over here, they're cliquey if they always run with each other. They're four very close friends, and they don't really run with anybody outside their own friend group there. That's a clique. There might be like one connection out of that group or whatever, but they're all highly connected. Right? A knows B, or A is a friend of B, B is a friend of C, C is a friend of D, and all of those combinations thereof. In a graph, that's a clique is vertices such that all of the edges are present in that subgraph. Right? They could be that this person knows this, and then there's another friend group over here, right? And then there's a friend group over here that 5 people, whatever, right? Whatever that looks like, right? Each one of these parts of a graph is a clique. This is a clique of size 3, clique of size 4, clique of size 5, right? But if I combine these two friend groups here, that's no longer a clique because none of these other edges are present, right? Finding whether or not there's a clique of size k, finding the maximum sized clique are very, very hard problems. But they can be solved using brute force algorithms that we've already discussed, and that's where we'll pick it up tomorrow. I don't see any other comments or questions on Piazza or YouTube, so I bid you a good day, and hope to see you in office hours if you're having any trouble.